All right. Hello, everyone. Good evening and welcome back. Today we are starting off with chapter 6, which is about perfect shuffles and a few other kinds of fairly systematic rearrangements of cards. And I think the way I'm planning to split up this discussion across two meetings is the following. So there seems to be one main effect that is described here with a lot of notes and variations and other things that you can do. And an explanation of why it works, which I have to admit, I understand about halfway through, I think. And that too, perhaps not very formally, but visually. And there is one last step, which I think we'll just try to figure out in real time. So that's the plan for today, to look at the main effect described in the book, which involves a few different kinds of shuffles. And then tomorrow we'll come back and I think formally define what perfect shuffles are and what a few of these other kinds of shuffles are that are involved in the effect that we will see, and the math of the kinds of properties that are preserved by these shuffles. So for example, temporarily just thinking of a perfect shuffle as a cut of the deck in exactly two equal halves and then riffling them in so that you have a perfect interleaving. So you have exactly one from the left and one from the right in every instance of the riffle, and putting this together, there are like a couple of choices that you have to make, sort of the so-called in shuffle versus the out shuffle. But for one of them, an example of the sort of thing we will talk about tomorrow is this idea that if you take a standard deck of cards and you perform a perfect shuffle consecutively 8 times, then you go back to where you started. And one of the things that they say in like the preamble to this chapter is people like if you were a gambler or something, if you could do perfect shuffles, it would be quite useful because let's say, I think the example they give is suppose you have four aces at the top of the deck, and you do like a perfect shuffle 4 times. Then what happens is that the four aces get distributed in the first, fifth, ninth, and 13th positions or something like that. And so if you were to deal out the cards into packs of four, then like we saw with the poker hand a couple of meetings ago, what's going to happen is all the aces land up in your hand if you're the first player. So that's the sort of thing that perfect shuffles could be applied for if that's your thing. But for today, I think what we are going to do is let me see if I can get my camera angle right. And if I can, then I just like to walk you through the main effect that they have and one variation at least, I think. And then from there, we'll basically, I think the main aim of today's discussion is to dig deeper into this, the mechanics of this effect and try and understand how it works. Okay, so it's not an effect that requires a lot of setup and it has only 12 cards. So let me see if I can get the positioning right. I don't think I'm sharing my video just yet. So just give me a moment. You can probably see my desk now, right? Okay. All right. Sorry, it's a little messy, but okay. So this is the deck that we're going to start with. Hopefully it's not mirrored so you can read off the numbers. Yeah, I think that's fine. Okay, so as you can see, this is actually a pretty ordered deck, and I think I have. I'm not sure if performatively you will begin by revealing. I actually think it doesn't matter so much. So you're going to tell your audience that this is how your deck is stacked. You have ace through six. By the way, this is very followable trick, so feel free to bring a deck, pull out the top six cards. Um, of your favorite two suits. And so basically any set of matching six cards will do. So maybe I'll just wait for 10 seconds here while you pull these out. So the way we want to stack these up is that the first six are the ace through six. Yeah. That's the top six cards. And then the bottom six cards is like basically six through aces. So the same thing, but in reverse. So this has the effect of, for example, the top card is an ace of hearts, the bottom is an ace of diamonds. the second card from the top is a two of hearts. The second card from the bottom is a two of diamonds. So this kind of an ordering where you have this kind of a symmetry around the middle, right? So if you were to draw a line here, you'll see that the cards can be paired up. This is something that they call, if I remember correctly, they call it a stay stack. So, so the idea is to think about shuffles that kind of have some sort of a mechanism for preserving the stay stack structure. So when you're starting off this trick, so the premise of this trick is the following. We're going to shuffle this a bunch. You can shuffle it as much as you like once you know that these shuffles are stay stack invariant. At some point, you're going to get the shuffled pile, and you're going to have a user, you're going to have your spectator choose one of these cards and set it aside. Then you're going to shuffle the remaining deck some more, and you're going to be left with the partner of the chosen card. That is the intended effect. So as an example, the user ended up choosing the ace of hearts. Whatever you do with the rest of the deck will somehow make the ace of diamonds emerge. Okay, with the original deck, maybe not such a big deal, but it can be impressive if you do it after like a whole bunch of shuffles. Okay, so give me a +1 if you think we are good to go, especially hopefully you've had a chance to pick up 12 cards. It's actually for 90% of the trick, you can make it work with any even set of cards with with a pairing between them. But it's recommended that you get 12 because like the very last step in the trick only works if it's 12, or strangely if it's 4 or 44, some such thing. So 12 is the most reasonable number to work with. Okay. All right. So thanks for the go ahead. So, okay. So we have this stacked deck. Let me just make sure that it is stacked as I want it to be. Okay. It looks reasonable. So the first thing you can do is pick a number 2, 3, or 4 and deal it out into that many piles. So for example, could do 2. And you can reorder them whichever way you like. So just like we did with hammer right in the beginning, you can fold left to right or right to left. As it turns out, it will not matter. Let's do maybe 4. So 12 divides evenly into 2, 3, 4. Could also potentially do 6 piles. We'll come back to a larger number of piles, but for now it's just easiest to think of it to do it as either 2, 3, or 4. So you could do this a bunch of times, as much as makes you or your spectator happy. Actually, there's also one of those effects where you can have your spectator do most of the work. It's fairly straightforward, and there isn't much danger of messing up. So you could give them control here. So, okay, so let's just maybe for completeness also deal it out into piles of 3. And as you would expect, 4 cards in each. And we reassemble those. Okay. So now you're going to do another kind of a shuffle, again, mostly to impress. So so this is what they call a reverse perfect shuffle because as they point out, a perfect shuffle physically is out of reach for most people. So we're going to do instead what's called a reverse perfect shuffle, in which what you do is you push up all the alternating cards. So all cards at even positions come up a bit, and all cards at odd positions stay down. Yeah. Was that reasonable? So just to do that again. So push out every alternate card. Okay. So you expect to have 6 cards on top and 6 cards on the bottom. And once you have done this, just pull out the cards that came out on top. Again, you'd expect that to be a collection of 6 cards. Maintain their relative order. You see 6 of them there. Maintain their relative order. And again, I think they recommend that the cards that you pulled out come on top. But if I'm not wrong, it doesn't matter. Okay, so that's what's called a reverse perfect shuffle. Essentially, what you're doing is collating all cards at even positions, pulling those out, and so essentially what you have is 1 3 5 7 followed by 2 4 6 8. A few more because we have 12, but yeah, that's essentially what's happening with the reverse perfect shuffle. Okay, so is everyone with me so far? Essentially, we just did like we took a stacked deck of 12 cards, did a bunch of dealings, after which we did a reverse perfect shuffle. Is that okay? All right, awesome. So, all right, so now what we're going to do is, okay, good. So, what we're going to do is, don't know how to pronounce this, Monge. Let's just double checking the name. Monge Shuffle? I'm not sure. Anyway, what we're going to do is the following. So this one may require a little bit of care, but essentially take the is in the reverse perfect shuffle the same as two pile? Yeah, I think yeah. So essentially what you do when you do separation and a perfect interleaving, I think that's what you get. So the reverse perfect shuffle I think has the same effect, but it's less painful to execute. Um,
No, it's different. The ordering of the numbers will change
right. So let's okay.
because your 1, 2, 3, 4 will go down when you deal it into two piles.
Correct. You're right.
And in the in
Correct.
the other
Correct.
case, those things will come up. Yeah.
Right. I think, yeah, you're right. So I think the actual ordering is going to be different, but in terms of preserving invariants that you care about in some sense, I think they are kind of similar. So morally equivalent, but not exactly the same. Yeah. Um, okay. Pratik, are you asking if we can deal them off into piles of two cards each, make 6 piles? I think you can.
The odd and even one that we did, right? That is equivalent of taking 6 piles.
I see. In terms of, yeah, the odd and even one was 2 piles with 6 each, and what you're saying is if you do 6 piles, you'll end up getting the same. Let me just check the. Yeah, it sounds like it should be. Let me. Right, yeah, for. Correct. For 6 piles, I think it's the same. I think we have to pay special attention to like a number of piles that doesn't divide evenly. So I think in their notes they say that if you want to do something other than 2 3 4 or 6, you have to be a little careful about in which order you collate the piles back to preserve the state stack invariant. So but you're right. I think for 6, it's basically the same. Yeah, good point. Thanks. All right. So okay. So once we've done the reverse shuffle and we've done the dealing and the reassembling a few times, hopefully your audience is convinced there's reasonably shuffled, and we're going to shuffle it some more. So take the top card into your other hand, and then start like uh, think of this as a sort of a central holding card, and then go up and down on the remaining. Okay, so take the top card off and distribute the other cards alternatingly, top and bottom of the top card. Does that make sense? So this is a Monge shuffle. Like I said, I'm afraid I didn't check how to pronounce this word. So this is a shuffle that we do at this stage. Um, Are we all comfortable with this? This is a point from where the user gets to make their choice. Okay, great. Thanks. So now the user gets to choose their cards. So to do that, they can take out as many cards as they like, pushing it to the bottom. haven't actually checked if, yeah, I think it shouldn't matter if they actually end up taking all the 12 cards to the bottom and then they take some more cards to the bottom. I think it's the same. So, okay, I took a few cards to the bottom. And at this point, we genuinely don't have a way of knowing what this card is, unless you have some amazing mental dexterity to remember what happened as the effect of each of those shuffles. We may have, like, underlying this deck, we may have some structural properties that were preserved, but I don't think it's reasonable to expect we know what this card is. We probably don't. Yet, what we are hoping to be able to do is find the matching partner card here. Okay. So after this under over kind of a shuffle, ask your spectator to pick a card by pushing any number of cards they like to the bottom one by one, and then dealing off the top card, and then they can see it if they like. You're going to keep it like this. And now here we're going to do something that's pretty much automatic. And speaking for myself, I'm going to pray a little bit and hope that we didn't I didn't screw up anywhere. But what you're going to do is deal off the top card and take the next card to the bottom. Deal off the top card, take the next card to the bottom, and keep doing this. Notice that this is an elimination procedure. We are getting rid of a card every time. And this is the part that requires the deck to have exactly 12 cards for this part of it to work. So we're left with this card. And so after all of this drama, we're really hoping that these two cards turn out to be the same. Yeah, the same in value. So they turn out to be partner cards. And this will reliably work regardless of how much shuffling you did. I think the only thing to track is to remember to do the shuffle where you distribute the cards up and down across the top card. That's the key step that makes this work, apart from the last elimination step. Of course, the elimination step's also an algorithm that essentially somehow discovers the partner card. But the reason the elimination step is able to discover the partner card is because that's how it got set up when we did the up and down shuffle, the Mongoose shuffle. Yeah. Okay, so mercifully this worked. Should we try and figure out what's going on, or should we look at a variation of this? We see if... Okay, let's look at why this works. We'll come back and if we have time, maybe look at a variation. So I have two ways of trying to show whatever little I understand of the mechanics. I do have a demonstration, which I haven't uploaded yet because it's kind of ugly and doesn't work very well. But what you see on your screen here, let me just refresh this. So this is our original stacked up deck. Yeah. And there's a little bit of a color coding to show you which cards are paired up. Let's see what happens when we deal these into piles. Actually, I think I'm afraid this is not actually very good. So I was really hoping to be able to do like play buttons so that you could actually pause the dealing and see what's happening at every step. So I think maybe we'll just do that on camera. But what you can maybe just observe is, assuming that you trust that this thing works as you expect it to, what you can observe is that after the dealing and the reassembly, it still has the stay stack property. It still has the symmetry. So the yellows are together. It's maybe a different symmetry compared to what was there before. But the point is that the paired up cards still paired up. Right? So what I really wanted to be able to implement is that when it's dealt into 3 piles, it pauses so that you can take a look at the stack. But I haven't been able to implement that yet. So we will instead just do it here. This is a poor man's attempt or a poor girl's attempt at trying to look at the mechanics. So I try to find, so these are, if you have OCD, you're going to be very disappointed. So these are, I had to find 6 decks with different card bags. I couldn't find them all that were the same size. So you're looking at 6 different card bags, and card sizes are also different, but hopefully you can distinguish like the colors. So we're looking at the back. I wanted to do it with just the cards face up, but I thought this was like visually clearer to see what's going on. Yeah. So this is a stay stack ordering. So let's just stack up the deck and let's look at what happens. I think the easiest case is when we distribute into two piles of 6 cards each. And I think, like Pratik pointed out, that's the same as 6 piles of 2 cards each. So maybe we can look at that back to back. So here I have my symmetric stack. Yeah. Let's deal this out into 2 and see what happens. So here we have dealt out the top half of the symmetric set into 2 equal halves. And what's happening now is you're getting sort of this mirror effect here. And now, so basically, I think the thing to note is that this stack here, I don't know if you can see the whole thing. Sorry for a slightly crowded space, but at least empirically, what is clear is that these stacks are reverse of each other. Does that make sense? So if this is 1, 2, 3, 4, 5, 6, this is 6, 5, 4, 3, 2, 1, right? And so it's kind of clear that when I stack this up, I stack that up, I could do this or that. I would still have stay stack symmetry, right? It's probably going to be exactly the same when we do 6 piles of 2 cards each. I think this is maybe even clearer that you get 1 to 6. And because its original symmetry was reversed, you get 1 to 6 and then 6 to 1. And now in terms of collecting these, you can either go left to right or right to left. So let's go my left to right. I don't know how that looks for you, but my left to right. When I do this, I know that I'm going to be stacking this up with that pair coming at the end. So I know this is stacked with that mirrored. I know this is going to get paired up with that. So I think it's kind of one of these visually intuitive proofs, which I think if I had to write it up, maybe there would be some ugly notation involved, but hopefully it's intuitive that it sort of works. Let's look at what happens when you do 3 stacks. It's also kind of visually, I think, nice. When you do 3 stacks, the top 6 get dealt out like that. And now you start going backwards. And again, what's happening physically, and again, I'm sure if we were to write this down in some general notation, it will add up and make sense. Have to be a little bit careful. Like for 12, I'm confident that converting this to notation will not be a big deal. But if you want to say that this works for any even number of cards, and if the number of cards is divisible by 3, this is exactly the pattern you'll get. I think that's still reasonable. So essentially what's happening is when you deal these out, if you look at every pile, the center one has local central symmetry. And that's going to, like, whether you do left to right or right to left, this is the guy that's going to get sandwiched in between. So that's fine. And now the left to right and right to left are exactly like what happened when we had 2 piles. They are reverse of each other, right? So let's say we do this first and pop this over that and pop this over that. Again, physically evident that you maintain the symmetry. If somebody has like a cleaner way of saying this that cleans up the argument in one shot, as opposed to saying, proof by staring, please let me know. I think what is going on here is kind of evident in a way that should be cleanly writable. I just haven't had the time to try and like make it explicit. But so in the book, I think it's a passing claim. It's a passing claim that, well, when you do these shuffles, then when you do the dealing, stay stack symmetry is clearly preserved. I think, if I'm not wrong, that's basically all that they have to say about it. Yeah, I think their proof is to understand, deal the cards face up and notice that symmetry is preserved. So their proof is also by staring mostly.
Maybe we should give the numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and then show that sum of those pairs is 13.
Is always
And so, yeah, so every time that is happening, and when you do it, either this doing 2 at a time, 3 at a time,
it will
they
not.
all
Yeah.
do the same.
Yeah, I think that's probably true. So this will be 1 plus 12.
Yeah.
This will be 2 plus 11, and so on. Yeah. Yeah, I think that would be a nice way of trying to make it explicit. I was thinking of using indices A1 to A6 and then B6 to B1, and trying to suggest that there is some sort of like they're suitably attached to each other. But yeah, I think basically you're right. You can sort of see that what's going to happen here, although technically I think this is going to be 1, 2, 3, 4, because that's how we dealt them out. 5, 6, 7, 8, 9, 10, 11, 12. So this is 5, and this is, yeah.
That's 5 and 8.
Correct. 5 and
Again, 13.
Right. Yeah, I think the point would be that the distance that yeah, it's sort of a rearrangement of 1 to 12. Maybe, I mean, I'm sure what you've said is true. The only question is, how do we describe why it's true always? It would probably be nice to have a one-line description of that. Sorry, a bit slow with the cards, but I think I'm just going to pull out 1 to 12 from another deck and but at least visually is the symmetry apparent? So again, these two are opposites of each other, and whether you go left to right or right to left, this is going to be the bottom of the stack, this is going to be the top. So they do mirror each other. Same for this. So if we are going, let's say, left to right, what is going to happen is we have this followed by this, so, and then followed by this. So that's generally speaking going to work. Let's see if we can do so. Yeah, we want Sunita, 6 ke baad 7, right? Not 12.
Yes, 6, 7, 8, 9, 10, 11, 12.
Yeah, so let's deal these out face up, I guess. Yeah, so now people are matched with 12 minus I minus 1 sort of a thing. So ace is matched with queens, queen 2 is matched with 11. So 12 minus 2 minus 1. 12 minus 3 minus 1 is 10, and so on. So that's the matching. So I guess what you want to say is, yeah, as you move down, you can see that all these sums, like if you have a 2-pointer kind of a argument, right? These sums are always 13 because you dealt off the, like in some sense, the gaps, right? So I dealt off 4 cards before I got to 5. And after 8 also, I have like 4 cards remaining. So there's some sort of a distance argument. Like if you were to write this in general, I think if you were to move your pointers up in whatever direction, you would see that like how far along you are from the left and how far along you're from the right is kind of equal, and that's why it should sum to a constant or something like this. Okay, so
So I think focus on a single card and its pair.
Sure.
And go modulo whatever you're doing currently.
Right.
Get 3 or 4 or 2, whatever, right?
Right.
and then ask where they land up.
Where they land up
It's
in the final
in the pile. Yeah.
Hmm.
Okay. And I think it is not too difficult to argue then that the
Hmm.
way whether you go left to right or right to left is completely symmetric.
Correct.
And
That
so then it's not
Yeah.
that difficult because
right. So okay, maybe let me actually do this this time just to make the partners a little more evident. Okay, I can't seem to find my low heart cards at all. Just give me a sec. I think I may have used up my okay, there we go. All right, so the way this is going to be dealt out, like if it was the first time, it would be something like this. Yeah, so the question is if you want to focus on an arbitrary pair and we ask ourselves, so in the original deck, for example, the 6 and 6 were in position 6 and 7. And when we deal them out and when we deal them out in fours and we reassemble them, so the 6 moves to, let's say we're going to do it left to right, then this 6 moves to position 4. And this 6 will move to position 4 from the top, which is to say, position 5, 1, 2, 3, 4, 5, 6, 7, 8. So this is going to be 5 and 8, which we know is like basically there are 4 cards left on this side. So so essentially we want to say that any pair of cards that were symmetric to begin with, when you deal these out, they're kind of, I mean, the way I want to see it is that they're equidistant in terms of like the number of cards that the first one has above it versus the other partner card that has coming below it, right? So for example, the 2, the first 2, like that came out in the dealing. Well, in the dealing, it came out second, but when we are going to reassemble, it's going to have 3 cards sitting on top of it. And the second 2 is going to have 3 cards sitting below it, or the other way around. So those 2 scenarios are symmetric. So I want to claim, and I think, of course, one can physically verify that this is true for everybody. So for the 3 of hearts, for example, we see that it's going to be sitting, assuming we go left to right, it's going to be sitting beneath 5 cards, and the 3 of diamonds will have 5 cards coming after it. So if you were to just do all the cases, you'll see that it's the same number of cards above and below. In terms of like a general formula for like if you were the ith card, let's say I less than the middle, let's say we're doing 12. So if I is at most 6, so the ith card from the left, okay, and let's say you deal into piles of 4 or piles of size 3, 4 piles. Then I goes somewhere and the mirror of I, which is whatever is, so that's n minus I plus 1 or something like that. So I goes somewhere, n minus I plus 1 goes somewhere in the final rearrangement, and we want to say those are also such that they're equidistant from both sides. So wherever I gets mapped to, n minus I also gets mapped in a symmetric way. So I think if we just write out what those positions are by like physically observing this, maybe like a pattern will emerge in terms of like you can write it as a closed form or something. So okay, for example, 1 is going to 1, 2 is going to 1, 2, 3, 4. 3 is going to 7, and 4 is going to 10, something like this. And the partners, for example, as we sort of know, I think the other 2 will go to 9 and so on. Okay, so I think that was Sunita's point earlier, that the position will add up to 13, which is essentially basically saying that your positions like, if your positions add up to 13, is that if and only if you are symmetric. symmetrically positioned. So like that's a nice way of trying to capture what's happening. So okay, so indeed, as I move my pointers towards the center, we see that these positions do add up to 13. This is 1 and 12. And I increment 1, decrement 1 in every step. So all these positions will indeed add up to 13, the final one being 7 plus 6. But if we have two positions adding up to 13, does that mean that they must necessarily be, I suppose, yes, because so for 3, for example, the unique thing that I have to add to it to make it 13 is 10. So that must mean that I am basically here. Yeah. So so if there are two positions that add up to 13, that characterizes the symmetric positions, the symmetric positioning. So now all we have to do is say that when you deal these out, right, what happens to the partners is that they go out to new positions, but they still add up to 13. Yeah, so I guess, yeah, maybe there's still a bit of a gap in terms of how to write that in proper notation. Yeah, let me think about that a bit. I think that's it's like an interesting thing to make formal. But I think as far as a deck of 12 cards is concerned, like we have physically fact checked that all the dealings into 2, 3, 4, and 6 piles preserve symmetry just by, like, you could say this is like case analysis, I think, by just staring at what happens when you do the distribution. And because state stack symmetry is like, yeah, I mean, once you start with a symmetric deck and you prove that symmetry is preserved, of course, this means that you can now do this any number of times and you'll be back to a symmetric deck. Okay. I think another thing that's nice to argue is that if you do the reverse shuffle, yeah, so in terms of formalizing what we just said, I'm going to leave that slightly open-ended because I think we have most of the main ingredients. Like I think Sunita and Vinay have already pointed out, ideas including the sum of the positions being invariant plus formalizing the mapping of where does position I end up in once you do the dealing into K piles. So when you deal into K piles, I goes someplace. So now if you can argue that whatever that mapping is sum of partners preserving, then you're in good shape. And we have only verified this manually. And for now, I'm going to leave it at that. But let me see if, yeah, if any of us have anything more concrete on this, I will be very happy to add it to the notes. Okay. All right. So let's consider what happened here. What we did was we pushed up every alternate card, right? So notice that the positions have opposite parities. Like Sunita is saying, they add up to 13. So for example, this is 1 and 12. This is 2 and 11. So all the partner cards have opposite parities in terms of what their positions are. And so when we lift up every alternate card, exactly one copy of each pair will move to the top, right? You're going to see no repeats. So for example, here my bottom card stays on top. This moves, stays at the bottom. My top card stays at the bottom, sorry. So for example, in the middle, where we had this middle axis of symmetry, one of them gets pushed to the top, the other comes to the bottom, and so forth. So what is kind of clear is the top set gets one copy of the 6 cards and the bottom set has the other copy. So that's definitely happening. Now, when we pull out everything on top, and this is why I said I think it doesn't matter whether you put which set you put on what. When you pull out everything on top, and then let's say you put it on top of everything. So the claim would be that the relative order of these cards, one of them is exactly opposite of the other, but that is kind of true because that's how stack symmetry was to begin with, right? So I don't know if that is making sense, but for instance, okay, so once we do this, we can have stack symmetry. So I think I can try to argue this again. But let's say we pull up here, for example, the blue card and the red card. The blue card and the red card, therefore, are going to stay put at the bottom half of the deck because we know, because they're paired up, we know parities are opposite. So if they got pulled up in the top half, they're going to stay put in the bottom half. And in the bottom half, they already occurred because the stack had stage symmetry or whatever stack symmetry to begin with. We know that they not only stay put, but they're staying put in the opposite order, right? And so this is true for, let's see, the first 3 cards that bubble to the top. It's true that their partners are going to stay at the bottom. In the bottom half, they're going to stay put. They won't bubble to the top, and they will occur in the opposite order of, of the cards that were pulled up. And now it's a symmetric argument for the other set. So here we have the black and the green and the colorful card getting pulled up. And we know that these 3 cards that are pulled up here, they stayed put in the top half, and they must have stayed put in the exact opposite order, again, by definition of the original symmetry. So when we pull these cards out, not only do we get one copy of each card, we also get it in the exact opposite order as the other half. Does that sort of make sense? At least this part seemed like, I mean, even if this argument is not terribly formal, it seemed at least intuitive. So let me know if you agree or if you think this deserves more justification. So what we are basically saying is that the reverse perfect shuffle preserves stack symmetry. All right, thanks. Okay, so I haven't actually checked, but my guess is that if you were to do a perfect shuffle, that would also preserve stack symmetry, or would it? So if we did I just said that the reverse perfect shuffle and the perfect shuffle are morally equivalent. We're about to find out. Okay, seems promising. Yeah, I think, again, argument along similar lines, I imagine, to argue that a perfect shuffle will also preserve stack symmetry. I think it's basically the same idea because you're pulling out, as you do this, what are we doing? We are alternating, alternating in some sense odd and even positions. And the relative order on one side is opposite from the other because that's how it was set up initially. I think it's more or less the same argument. Yeah, don't quote me on that maybe, but I think that should work. Okay, so the reverse perfect shuffle and a perfect shuffle will preserve stack symmetry if you already have it. So you can do that freely. Now, like I said, we're not done yet. So this was like, so I think this trick happens in basically 3 phases. So initially you do all the shuffling, the dealing, and the perfect reverse shuffle, the reverse perfect shuffle and the perfect shuffle. You can do all of that as much as you want. And you know that you'll still have a deck which has stack symmetry. Now, when you feel like the deck has been thoroughly shuffled, you do this thing where you do we said we'll take off the top card and we'll go under and above. So I actually encourage you to do this with your own deck. So this is where we come to the middle of the deck. So when we are going under and above, so what happens, you think, to the middle 2 cards? Like they get separated now. And notice that they've been separated. So when I put this card on the top, I'd already dealt out 5 cards because this is the 6th card and this is the 7th one. So I already dealt out 5 cards before pulling this on the top. And now this goes on the top and this is a symmetric partner. It goes to the bottom. So notice that there are exactly 5 cards between the 2 middle cards, right? And now it turns out that this is going to continue being true for all the other partner cards. So if I were to pull these out, and hopefully almost all the cards are in frame. Yeah, sorry that the lighting is super awkward and getting a lot of glare probably, but okay. So if you take, again, this is something that I can only say, well, I mean, so again, more or less a physical proof. If you basically take any of these partner cards, you'll see that there are exactly 5 cards between them. That's what the over-under shuffle does. Yeah. Okay, Sunita, you're saying the composition is an identity. Oh, you mean when you compose the reverse perfect shuffle and the perfect shuffle, you get back what you started with? I see. I see. That'd be a nice thing to verify. Yeah, maybe.
I think. Yeah. So before I just forget, I mean, there's an interesting problem that we have 2 n cards, right? They're n factorial symmetric things, right? Because you can fix the first n factorial and then the remaining n factorial have to be mirror reflection, right?
Correct.
I don't know whether whatever you described so far, whether that's actually a generator for all possible such sequences. So that may be an interesting thing.
Yeah, that's a nice question. So what you're asking is, can all the stack symmetric permutations be accessed only by
realized.
a combination, right?
So
Only
these
by a
become the
combination
generators
of
for that.
right. Yeah, that's okay. That's yeah, I don't think this is something that's addressed head on, but I actually have to confess that I haven't read the whole chapter just yet, so maybe it is. But it's a really nice thing to think about. So because that's been a common theme for Gilbreth and Hammer and maybe even De Bruijn to some extent, the question of now you have a class of constrained permutations and you have a set of operations, like how many of those permutations that you care about can you actually reach using these operations? Or actually, so far it's just been given a set of operations, what are all the reachable permutations? Yeah. So here, right. So we know that these permutations preserve stack symmetry, so there's no hope of getting out of that set if you start with something stack symmetric, but can you actually get to all of them? Yeah. So, all right, noted. It's definitely something to think about. Okay. And I think, Sunita, your point seems valid too. It's just that I think just don't have the mental agility to validate an example off the top of my head, but let's just come back to that with an actual example to be sure. But yeah, it seems to intuitively be appealing that that when you do a reverse perfect shuffle followed by a perfect shuffle or the other way around, you get back to where you started. Right. All right, so this, okay, so the under and overhand, they have the effect of, I think now we see that we do not preserve stack symmetry anymore. We have finally destroyed that, but the property that we now have, which is useful for the trick to work, is that all pairs are separated by 5 cards. So blue and blue, you have 5 cards. Red and red, again 5 cards. So you just keep moving and you see that you have 5 cards between all the pairs, right? Okay, so I think now we are ready for, okay, the part that I said I like. Yeah, I mean, it's obviously everything I've said so far, it's not clear that I've understood well, but the last part is actually even more of a mystery than the rest of it. But anyway, let's consider what the user does to select their card. They are allowed to take as many, for as long as they want, they can keep pushing cards to the bottom of the deck. Notice that this operation preserves the distance 5 property. So as long as I'm pushing cards to the bottom of the deck one at a time, if all the pairs were like 5 apart to begin with, they continue to be, and this is also a function of the fact that 5 is like basically, other than the 2 cards that you care about, you have 10 cards left, right? So so if I have 5 in between here, I must have 5 at the bottom. So when I push this card to the bottom, I again have 5 between the 2 reds. So hopefully that makes sense. So at some point, the user decides to pull out a card and they say that's their card. And now from here, we actually know that the partner card is 5 from the top. Okay. At this point, you could actually just like pull out 5 cards and reveal this one. And I think that would be a match, and that would probably still be impressive. But I guess this one's even more impressive, that this elimination actually works. And I think it's important that the first card goes to the bottom. Like, I think if you do it the other way, it won't work. So let's consider what's happening here. So in my first, so I have how many cards here? I have 11 cards. So in my first round, I'm going to be getting rid of the first card, the third card, the fifth. Hopefully, yeah, the fifth. Okay, so I have 5 cards. I know that like the top 5. I know that after the top 5 cards, I have this one. So in my first round, I'm going to eliminate the first, third, fifth. This one's going to be safe. Then the 7th, the 9th, and the 11th. So all of those are going to go. Now in the new ordering, okay, so maybe let's just do that. So this is first, this is third, this is fifth, this is the 7th, this is the 9th, this is the 11th, right? So all the odd indexed cards are gone. Now I think this fellow lands up, I think this will always happen, lands up in the middle. Actually, in the beginning also it was in the middle. And I think that's kind of an invariant. Yeah, I suppose that's true, right? If you pull out like, okay, your desired card is in the middle, and now I've pulled out all the odd indexed cards. That means I have shoved away like an equal number of cards from the top and the bottom of where this guy was. So now again, what's going to happen is, okay, I'm going to put, okay, I forgot what I did at the end. So I think I take this back. Okay, so now I think the parity is going to reverse because I think I put this down, right? I did put that down. So yeah, that was the 11th card that got put down. So now I'm going to get rid of the 2nd and the 4th cards. That's what's going to happen. So that goes down, goes away, that goes down, that goes away. So the 2nd and the 4th cards are gone. That always works. I think I can sort of see what's going on in like the first phase of the elimination. In the second phase, that's when the odd cards go away. In the second phase, the even cards go away. And the card that we care about is like the third from the top. And now you can just physically see that if you do the elimination, this is the one that emerges. So let me tell you what the comment is in the book. The comment in the book is that like everything we did up to yeah, everything we did up to this last elimination step, you can do it with any deck with an even number of cards. But for right, for the last step, that would work if you had a deck of 4 cards or 12 or 44 or 172 and so on. So the kth term of the list of valid cards is obtained by adding 2 to the k minus 1 to the previous term. So the smallest deck with which this would work, which I think we saw maybe just now. Actually, I'm not sure. Okay, so if you had a deck of 4, that means you would have perhaps eliminated 1. You would have a deck of 3 or something like this. So put this down, let this go to the back, put this down and whatever. So yeah, okay. So it works for 4. That's a base case. Like if the original deck had size 4, the user picks a card. You're left with 3, and this I think is really like a base case. If you have 3 cards, and your card of interest is sandwiched between 2 cards, then this elimination surely works. So this is fine. Now they're saying add 2 to the k minus 1, which is like, so the second term is obtained by adding, okay, so starting at 4. So of course, if you add 8 to 4, you get 12. So that's k being 4. That doesn't make a lot of sense, but okay. So there's some pattern here. There's some pattern to like, if, okay, so I think here is the problem. The problem is that your card is in the middle. I think this is something that you always ensure. I'm ignoring stack symmetry for now. The card you care about is in the exact middle of an odd size deck. And what you want is for this elimination algorithm to surface this middle card. So for what sized decks would that actually happen? And the claim is that there is like a recursively formulated list of numbers for which the elimination would surface the middle card. Okay. I don't know why those numbers, like, I mean, 4 and 12 is just clear by observation. Again, it's one of these like physical things that you can check. The next number being 44. Yeah, again, like I don't know what's the general argument for generating that particular list of valid numbers. So I think that's one nice thing to think about as well. So this is the part that I said was a bit of a mystery to me. But the point is that this works for a deck of 12 cards. And if you want to up your game, then you can do this whole thing, but with 44 symmetrically matched pairs, the same thing would work. It would probably just be a little more tedious in terms of taking more time for everything to go through. Okay, but give me a +1 if the mechanics are okay, like the overall effect. So hopefully that made sense. And I think some aspects of like how and why symmetry is preserved, and how you get the pairs to be 5 units apart. I think most of that is at least clear at an intuitive level. I think it's probably a little more work to formalize it properly. But the last part, where if the card you care about is right in the middle of an odd size deck, the fact that there are only certain sized decks for which the elimination algorithm will surface the middle card. And how do you get a closed form for like exactly the set of numbers for which this is true? This I'm like kind of clueless. So I don't know what's going on there, but it would be nice to sort of figure that out. Okay, so I promised you that I'll show you variations in a couple of minutes. Yeah, I realize we're close to the hour, but okay, in the book they have several notes about variations and other things that you can do with this. I think if yeah, for all the with a little bit of imagination, you can imagine doing like some of the variations are more cosmetic or aesthetic. So, for example, instead of doing this with a deck of cards, you could have the pairs be things like, Romeo, Juliet, Heer Ranjha, things like that. And you can make up some story about how you're going to make these lovers meet or something like this. So some of the variations are along those lines. But here's one where the effect itself is, I think, a little bit different. I don't remember if hopefully I've stacked this up correctly. So let's just hope for the best. So essentially, you can start with a 12-card packet, and the spectator can cut it anywhere they want. So remember, in the other one, we didn't have a cut, we only had dealings. But again, the spectator has a free choice. They move cards top to bottom as much as they want. At some point, they stop and they pick out one card. And now we are going to do our elimination. Let me try and make sure I do this right. Okay, so the elimination reveals one card. But what we are going to do, all right, so that's my reminder to maybe wrap up, but I'm going to take just a couple of minutes more. So what we're going to do is now we're going to actually, the performer is going to continue from here. And we're actually going to do, like, maybe you could pretend that you're just casually moving cards from top to bottom. But I'm going to move, hopefully, 5 cards from top to bottom. And I'm going to pull out one more. And now we're going to do elimination again, but this time, instead of putting the first card at the bottom, I'm going to put it down under and then go to the bottom. So it's reversed. And again. All right, this is something that I expect will only, like, I'm not sure if this will work because I don't remember if I had set this up correctly, but the hope is that this time you've pulled out 4 cards, and the hope is that the cards are one of a kind, so they're all kings. Yeah, so that's this variation. I think the main differences in the two effects is that in the first one, I think you have a lot of the dealing and the shuffling and all of that that's eliminated. Here you just have one free cut, and the user chooses a card. And then you just take it from there. You do the elimination. You do the first elimination, get 1 pair. Then you move 5 cards to the bottom, pull out another card, and then do an opposite elimination, where in the first step, instead of putting it down, you put it under, and then you do elimination again. And you would have pulled out 4 cards of the same type. So here again, probably nice exercise to figure out why this variation works. I think it's again along very similar lines, but here is how you set up the initial deck. I don't think it matters if the suits are mixed up. Haven't actually checked, but yeah, so this is the initial ordering of the cards. And if you start with this sequence, so this is unlike before, which was stacked. I mean, you could argue that there's also some kind of stack symmetry. Actually, not very sure, because in some sense, if you care about, like, if you think of pairings, it's actually not stack symmetric, because these are not the same, like the top and the bottom cards don't have the same value or the same kind. They're not similar in any way. So anyway, I think, but a lot of the principles, I think, basically similar. So you have king, queen, jack in a repeating pattern, and that's your initial deck. And we could try to figure out why this works. I think, given the time, maybe we take that offline. Like I said, I have mostly like a somewhat physical validation of what's going on. I don't have like a more general explanation. But that's kind of, even that I think is kind of fun to just play around and figure out what's going on. But performatively, I think this is all you need to take this trick to a classroom or a dinner group or whatever. So you have, just to recap, you have this deck set up in this order. Give it a free cut and have the user make a generally free choice. So it's a free cut and a free choice. So the spectator can pull down any number of cards they want and pick one. And what you do after this is going to pull out, like in this case, the user happened to pick out a queen. You don't know this, but the algorithm will reliably pick out the remaining 3 queens. So that's the effect. That's the variation. I think this is the only variation they have listed, which is like kind of non-isomorphic. I mean, that's significantly different from the base trick. The other thing, of course, is I think they point out that you could deal into a different number of piles, but they will not probably be the same size. And they leave it as an exercise to figure out, if you deal into a different number of piles, in what sequence should you pick things up so as to preserve stack symmetry. So that requires some homework and practice, but the advantage is that you could, you could ask the audience, how many piles do you want me to deal this into? And they could pick any number they want, and you can probably run with it. Yeah, I think their point is that, okay, another remark that they make is, often when you perform a trick, you're asked to perform it again. So here, if you think about it a little bit, it's not very hard to, like, even though we messed around with the deck a little bit when we did the 5 distance apart thing, I think they point out that you can do a little bit of a rearrangement and quickly restore the deck to being stack symmetric again, and you're ready to go once more. So that's, I think, another remark. And there's some very interesting historical notes about how this particular sequence was initially a sleight of hand trick, but they evolved it into this self-working version after some back and forth between a whole group of people. And so actually, I think the whole book is littered with a lot of these kind of really fun anecdotal stories about how tricks came about and how they were refined and how they evolved over the years even. So those are, like, I think I'm really not doing justice to pointing out the stories, but there's some really nice, there really some good historical notes and pointers here. So so if that's your thing, definitely take a look. I'm not really recollecting all the fun stories that are in the book. But okay, so this seems like a nice place to stop. Any comments are welcome. The plan is to, like, I don't think I have new effects for tomorrow. The only other effect suggested in the chapter, as far as I can tell, is a way to set up the deck so that you can always win a game of Faro, which seems like a betting game. And unfortunately, I just have not been able to parse the rules. I've tried looking at the Wikipedia page. I think if I can understand the rules, I will try to present the effect. But if not, I think we still have plenty to talk about in terms of the math of these shuffles. So that's the plan for tomorrow. And a couple of nice pointers and questions from today's discussion, which I will try to add to the notes. And I think what I will do is tomorrow, once we are done, I will hopefully, at least by tomorrow, update all the notes on the website and send you an updated link so you can revisit any of this whenever you like, for whatever it's worth. Yeah. Okay. So so any final questions, comments, suggestions? All right. So, well, in that case, thanks so much for the very nice discussion. I think just quickly remembered from the chat about the point of the composition being identity. I think it'll be a great thing to pick up tomorrow as we go through the structure of these shuffles. So, so if I forget, Sunita, please remind me to pick that up tomorrow. Just do a double check. Yeah. All right. Thanks very much, everybody.